So good morning and welcome back. That was fun. Great job to all of our poster presenters. Thank you for your ideas and your enthusiasm, and thank you to our awesome MC, Denise. What a treat it has been to be here in person this week. For me, there's some things I think that it's going to be a long time before I take them for granted again. And being here in person is one of those things. The ESIP staff and our board started this week with a meeting on Monday, and there was a moment in our board meeting where I just heard the awesome sound of blended laughter. There were 15 people in the room, but it was one sound of combined laughter, and it was really joyful. And for those of you online, we miss you. We wish you were here. Zoom has not figured out how to blend voices in that way. And to me, that's part of community, right? This week, that sound of combined voices I felt grow over the week. As I stood in the research showcase, I think I was talking with Sarah and Andrea, I paused for a second, and just the buzz of the room, the buzz of so many voices, passionate and excited about the work that we're all doing, all combined, it was really electrifying. And then yesterday, I think there was this really loud sound in this room as we were all gathered, but I think that was the sound of chattering teeth, because it was so stinking cold. But what I loved was that we came back to the afternoon sessions after some of you had been outside, and you came back into the cold, right? You came back to continue doing the work that we do. And that was really awesome, and I thank you for that. So meetings like this would not be possible with the help of so many people, and I want to thank our federal sponsors, NASA, NOAA, and USGS. I loved hearing that a lot of our federal sponsors this week used this time to gather in person with their teams, which are maybe a little bit more distributed than they were 3 years ago, and that we were able to provide that opportunity to come back together. I also really want to thank our meeting sponsors, AWS, Esri, and Element 84. I said it before, but meetings like this are not possible without this kind of sponsorship and support. And last night at the Funding Friday poster making, I was sharing that these sponsors are really engaged deeply with ESIP. It is not a transactional relationship they have with us, it is transformational. They are leaning in participation, in giving their people, in sharing their product, and it really makes a difference with the support that they give, so I want to recognize that. I hope that over the week you have all gotten a chance to know the ESIP staff. Allison, Barr, Annie, Megan, Patty, they are really a phenomenal team, and they're really incredible human beings, and I hope that you've gotten to know them a little bit more over the course of the week. I also need to thank the ESIP's board of directors and our elected leadership. They stepped up and lent a hand in so many ways, seen and unseen. If you like being in boardroom meetings where there's a lot of laughter and fun and hard work, I challenge you to think about ESIP elected leadership. Contact a member of our board or staff, especially Sarah Ramdeen, our nominations committee chair. We need elected leadership in ESIP, and we would love to have new faces and new voices at the table there. And lastly, a huge thank you to our community fellows. If you were in a session this week where someone unmuted on Zoom or screen shared or made those logistics happen, it was because of our amazing community fellows. This meeting started as a primarily in-person gathering, and I will confess there was scope creep into the world of pretty close to a hybrid meeting, and that was all due to the thanks and the help of our really awesome community fellows. They didn't go to school to be AV professionals, right? But they learned these skills and saw how that is important to community management and to make things work. But I hope that you can also engage with them on their research and their work. The goal of the Community Fellows program is to show them community management, but it is also to give them the most supercharged networking experience they can possibly have. So I encourage you to interact with our community fellows over the rest of the time today and throughout the year. So what is next? We have many great more sessions today, so don't let me move on too fast, but please save the dates for our 2023 meetings. Our January meeting, no, it was not yesterday. It actually was not January yesterday. Our January meeting will be fully virtual to provide an inclusive environment and increase our outreach, lower our carbon footprint for so many reasons. But then a year from now, we are really excited to finally be back in Burlington, Vermont. The long-awaited Burlington meeting will be next year. It's really important that we hear from you about your experience here this week. Meeting evaluations will be going out, and we really value your feedback. We want ESIP to be data-driven, so we need you to provide us with the data about this meeting so that we can use that to help shape and inform and design our future meetings. So please fill out those meeting surveys. It is really important. Remember that our work doesn't end here. ESIP works to bridge your organization's domains and work 52 weeks a year. If you're inspired by the sessions this week, we invite you to join the related clusters and keep the conversations going. To learn about all that is going on at ESIP, the best way is to sign up for our once weekly email, the ESIP update, and other information you can find on our website as well. So now, on to our speakers for this morning while we count the votes for the Funding Friday posters from this morning. It is my great pleasure to introduce this year's Robert G. Raskin Scholar, Colette Brown. Rob Raskin was a mentor to many aspiring earth science data professionals. In collaboration with Rob's family, ESIP remembers Rob and his dedication to support the next generation of earth science data and technology leaders through the Robert G. Raskin Scholarship. The scholarship is awarded annually to an individual in the earth or computer sciences who has an interest in community evolution of earth science data systems. The Raskin Scholarship seeks to promote collaboration, research support, and exposure for talented students in the earth or computer sciences. This year's Robert G. Raskin Scholar is Colette Brown. She is a graduate student at UC Berkeley Energy Resources Group, where she studies how to use remote sensing to expand plant survey assessment after tundra fires. These Arctic burn scars are hard to reach, but are part of one of the most impacted landscapes from climate change. Her enthusiasm for connecting climate and ecosystem data with remote sensing and ML make her a strong contributor to the earth sciences data community, and we are excited to welcome her to ESIP. It is my pleasure to present Colette with the Robert G. Raskin Scholarship and Award and hear more about her work.
Thank you so much, Susan, and thank you so much, everyone. I'm very excited. This is my first conference and first presentation, but I don't think there is anywhere else or a group of people that I would rather have this experience with. As Susan mentioned, I'm going to be talking about the work that I've done this past year, specifically focused on the Anaktuvik River fire and my work with NG Arctic. So I first want to thank you. The first and foremost is for this scholarship. I was able to do fieldwork this summer because of this scholarship, and it's been immensely impactful to be here this week. I also want to thank the scholarship committee and Megan, Allison, Patty, Susan, sort of everyone who helped so much to help me get here. The ESIP community, I think I asked maybe 10 people this week if they had advice for first-time conference goers. Every single person said, you don't need advice because everyone here is so friendly that they will kind of guide you through this weekend. And that has been immensely true. I feel so grateful for that. And then the last is NG Arctic and my field team and my research team that's helped me with this work and presentation. So this is a photo of me this summer. in Alaska outside of Nome, and I kind of wanted to give you a background of what I care about and what my research is. So in the background is the Arctic. I work just below the Arctic Circle, but broadly in polar regions where there's continuous permafrost. So everywhere that you walk, anywhere from a couple inches to a couple meters below, the Earth is completely frozen. I study vegetation, so specifically after burns. I really care about data science and like using machine learning, but also care about being a data provider, so going to the field, collecting information, and then sharing it with others. Collaboration, I got to go with a great big group of people to go do this work. And then the last, outside of science, I love to sew. I made some of the gear that I wore this summer in fieldwork to kind of stave off incredibly pesky mosquitoes. So I care about the Arctic because there are so many questions about whether or not the Arctic is going to be a source or a sink of carbon. One of the reasons why we still have this lingering question is because of these really big disruptions or perturbations that happen. You can see from left to right, permafrost thaw, permafrost slumping, which is causing impacts to infrastructure that the US and Alaska alone estimates will cost $5.5 billion. In the middle, we have tundra fires. As we have storms and lightning, we're seeing fires that are bigger, more severe, and longer lasting than ever before. And then the last is shrubification. So this means that where tall woody shrubs grow is starting to expand much more north, and they're becoming a lot bigger. And so what I care about is tracking how these shrubs are growing and influencing ecosystems. So you can see a photo here between 1966 and 2009, how even without a disturbance, shrubs are beginning to colonize entire ecosystems and completely transform the soil temperature, the depth of permafrost thaw, all of the other plants that are growing there. But my question is, how do we know that shrubs are expanding? And there are sort of three ways that we think about this. One is field measurements, and this is incredibly challenging because the Arctic is really hard to get to, especially in places where some of these disturbances are happening. It's really costly, it requires a lot of training, and you can only go during a couple months of the year. The second is satellite imagery. So we do things like measure peak greenness, follow NDVI. And then the third is Indigenous knowledge. So the Alaska Native corporations have a lot of local observations that they've been tracking for thousands of years, as well as just individual experiences of seeing these shrubs expand. So the research that I did was trying to focus on one location, kind of combining these three different types of knowing. The first was field data. The Bureau of Land Management set out 30 transects in the site of the Anaktuvuk River fire, which was the largest and longest burning fire that we've ever seen in the Arctic tundra. They went out for about 5 years and set up these different permanent sites where they got a bunch of vegetation data. So this is an example of what the ground looked like and how it transformed between a year after the fire to 10 years after the fire. So you can see that it's a really high severity burn, but then the ecosystem recovers. But the question is, does it recover in the same way? Do shrubs grow and expand? What do we see after fires? But it's really hard when you only have 30 transects and people going once a year to collect data. You can't really conclude anything about how vegetation changed over this whole burn scar. So I turned to remote sensing, and I worked mostly in Google Earth Engine, ran into a couple problems because they don't do time series machine learning quite yet. So a lot of downloading data, and I loved a lot of advice this week was just put it on the cloud, get it on the cloud. So I hope for my next project that will be possible to work exclusively in the cloud. But for now, we also just worked with Landsat 7, where a lot of people know you do have incredible amounts of data, but also with the sensor malfunction, you have a lot of missing data. So that was one of the biggest problems that we ran into. And then my question was, how can we bridge the gap between this field data and the remotely sensed data? And maybe the obvious answer to some is machine learning. So this was, I think the way that I thought about it and how I explain it to my family or cousins or whatever is when we see things on the ground, and then we also know that we can see things from satellites, how do we find a way to be able to connect those so that the satellites can essentially see what the human eye can see on the ground? So the methods were that we did our data acquisition from the Bureau of Land Management, a lot of preparation and data cleaning. We trained multiple machine learning models. We tested about 5 of them. And then we classified the accuracy of each of them individually, compared them, and then trained our final model to produce accuracy and predict across Beyond just those 30 points, across the entire burn scar between 1999 and 2020, to get the first ever really comprehensive vegetation map of before and after a high severity fire in the tundra. So you can see here, the plot shows the different classes that we used. We had 7 classes, as well as how many samples we had in each of them. So our data was really heavily skewed. Out of our 520 points, a far majority of them, I think over 60%, were in the substrate, so sort of exposed soil and graminoid classes, which are these like big grasses that grow and form tussocks and make it really hard to walk in the tundra. And with this data, we got really bad results. We had about 40 to 50% accuracy, but then we decided to resample with replacement to create a uniform distribution of our different samples that we had. And in the end, we were able to get pretty good accuracy. So you can see here the chart on the left shows when we ran our model 500 times using different seed values, it shows the validation score, and you can see that the average validation score was 0.84. So 84% of the time, we were able to accurately predict which class of vegetation is present in an individual Landsat pixel. And then my favorite chart is the one on the right. So this is a variable importance plot, and you can see on the x-axis all of the variables that we use to make our prediction, which include all 7 bands of Landsat, EVI, and NDVI, and then their importance. And with this chart, what's important is a little bit less what those absolute values are and more their relative importance to each other. And we were shocked to see this graph tells us every single variable that we use to try to predict vegetation was helpful in our final model. So it meant we weren't using any superfluous data, we were only using things that were very helpful. And it meant, I think my hypothesis based off of this is at what point, or which of these variables is helpful within the burn scar versus outside of it, what is better for identifying burns and regrowth after versus just continuous vegetation. So this is a map that was produced after we predicted across the entire landscape. And even without an outline of the burn scar, you can see in the blue that is all of the area that was burned in 2007, and then this shows in 2008. And you can see it's almost completely substrate. And then again, we see 10 years later how the vegetation has rebounded, how you still have these waterways defining the area, but you can see some of the growth as well as some mosses, and it's a little hard, I recognize, on there. So a bit of an easier way to see it is how this change happened in the percent of land cover every year. So when I looked at this graph at first, starting in the year 2000, the percent of land cover was really, really low for all of the important shrub classes, which are the SSE and SSD. And then you see they grow a little bit until 2006. But then in 2008, a year after the fire, there's a really sharp increase in the number of shrubs that are growing in this area. And I was like, great, this is amazing. I'm so happy. We've shown shrubs grow back after fires. This is an incredible feedback loop we've identified. And then I plotted again in 2018, and you see that the shrub population declines again. So what this showed me is that there's a lot more research that needs to be done, that it's really cool that we see a year after fire, shrubs kind of colonize some of the landscape, and then they start to disappear. And we don't really know why, and we don't know if this will lead to more fires in the future, so it led to more questions. But my conclusion was that immediately after fires, shrubs do come, and they probably alter the landscape in some way. They have the potential to be really insulating on the ground and increase the temperature underneath the shrub by about 30 degrees Fahrenheit between areas that are not within shrubs. And then the second is that every piece of data from the field is helpful when building machine learning algorithms. We saw that with a resampling technique, we increased our accuracy from about 40 to about 80, which was pretty cool to see, but with more field data, I imagine that could be higher. The third is going back to the 3 types of knowledge. So when you think about working in the Arctic, and specifically in Alaska with Alaska Native corporations, there's a big question of what is the line between doing environmental science versus engaging with communities. So for our work that we did in the Anaktuvuk River fire, you're in the North Slope Borough, which is the least populated but largest county, all above the Arctic Circle. So we weren't close to very many communities, kind of no permanent settlements. So we didn't work with Indigenous communities there. But as I continue thinking about the work that I'm doing, there's a big question where a lot of these groups really focus on lichen, because reindeer come and they get lichen and they eat it, and then the indigenous communities can use that as subsistence. And with climate change, lichen is both disappearing and is frozen underneath when you have snow and they can dig and get it. And then when it rains and it freezes, it's just a layer of ice that is blocking any of the animals from being able to eat anything that they have for thousands of years. And this is it's incredibly interesting for subsistence, but it's really hard when scientists care about shrubs. Lichen are a very small part of the ecosystem. So there's sort of this fundamental divide where lichen does not equal shrubs, and where a lot of the funding that we're getting in the Arctic isn't in line with what the communities that we are working with need us to be doing. So I think my biggest takeaway is that we know communities need to be engaged early and consistently, and that they can't just be used as a token of we talked to them, they said that they need lichen, well, we don't have funding, we're gonna focus on shrubs, but at least we know now. Instead, we need to engage with them before the funding process, before the proposal process, to ensure that they're part of this work every step of the way. But I still have a lot of lingering questions, and these kind of came up throughout this week of when is it necessary to work with communities when you're doing environmental science? If you're in the middle of nowhere, if you're far away from them, if you're getting permits to work on their land, is that as far as you need to go, or is it always a prerequisite to work with the closest communities in order to conduct effective science? The second is how do we genuinely and effectively incorporate these communities from the very first step? And then the third is, I think this came up the most in terms of logistics. Of someone mentioned with NASA, you have a year timeline or 3 years on a grant, and then you leave a community hanging high and dry. What do you do? So for me, as I embark on my next stage of research and thinking about how do I ensure a sustainability plan, that every time I enter these communities, so what, I have good intent, I want to do best by them, but what does that mean when I can only work with them for 3 years? How do I ensure that my research is engaging and effective and helpful for those communities? So with that, thank you so much for listening. I'm so glad I got to share, and I think now it's Q&A.
Thank you so much, Colette. I love that she ends with as many questions, you know, that the journey keeps going. So you guys know the drill. Go to Slido and put your questions up there. We have time for a few questions, and I'll start with the first one. Do you know if shrubs, especially young plants, are more vulnerable to extreme cold weather events?
So one thing about shrubs that's very different than other plants in the Arctic is that they have the capacity to hold a lot of snow, and snow is really insulating and really protective. So when you have these really intense winds that are blowing through, the snow and their like woody and fibrous branches and stems are able to protect them a lot. And so I think they're not as vulnerable to things that typically keep other growth forms really low, which makes them, in my view, less susceptible to cold weather events. But I don't know in the absolute, like when it gets to minus 60 degrees Fahrenheit with high wind, I'm not sure. That's a good question.
Great. Can I get this Slido back up? All right. What responsibility do you think researchers have to shift their research in order to work with Indigenous communities? Thank you, Renee.
Thank you, Renee. I think it's imperative. I feel at kind of a constant conflict between the work that I care about a lot, which is helping to build more accurate climate models, which help on a global scale with policy and sort of changing things in the long term, versus working with these communities. Because I'm not a social scientist and I don't have a lot of the expertise, and the places that I'm funded from also don't fund that expertise to be on our projects. But that doesn't mean it's any less important. It just makes me question, I think for me, it makes me question what place I want to have in this work. And when I think about doing environmental science, yeah, but I think it is important. And especially in Alaska, where the structure of Alaska Native corporations is very different, I think it's already a lot easier to do that. To work on any land, we have to get sort of an access permit from any of the communities that own the land that we will be working on, which meant during COVID, you can't do any field work. No one visited for over 2 years because none of these communities wanted you to bring COVID in. But I think it's imperative.
Excellent, excellent. I know there are a lot of other great questions. Really amazing first presentation. We're going to end on a comment, even though, you know, Slido's not built for comments. Fantastic
Thank you.
job. I really appreciate that. We'll try and get the rest of the questions to Colette so she can connect and answer those for you. I think you can see, if you look at ESIP's strategic themes, we have some themes and some goals as a community to foster this profession of earth science data professionals. And I am so thrilled to have Colette here. I am so grateful for the Raskin Scholarship that allows us to cultivate this next generation of professionals. And I think you can see from Colette's presentation, we are in good hands and there is some great talent coming up. All of those of you that are hiring and have great positions open, I encourage you to look at our community fellows, look at our Raskin Scholars, because we've got some really great talent right here in our community, and help us attract that next generation and spread the word about those. So next, it is my pleasure to introduce this year's Falconburg Award winner, Ryan Abernathy. Ryan is an associate professor of Earth and Environmental Science at Columbia University and Lamont Doherty Earth Observatory. He is a physical oceanographer who studies large-scale ocean circulation and its relationship with Earth's climate. He received his PhD from MIT in 2012 and did a postdoc at Scripps Institution of Oceanography. In addition to the Falconburg Award, Ryan has received an Alfred P. Sloan Research Fellowship in Ocean Sciences, an NSF Career Award, and the Oceanography Society Early Career Award. He is a member of the NASA Surface Water and Ocean Topography Science Team and Director of Data and Computing for a new NSF Science and Technology Center called Learning the Earth with Artificial Intelligence and Physics, LEAP. In 2016, he helped found the Pangeo Project, an open science community focused on big science data analytics. Ryan.
Okay, great. What an amazing talk from Colette. It was just so inspiring to see. It's a very tough act to follow. I'm going to go in a very different direction. It's great to have this platform to be invited to give a talk that's not about any sort of specific research project, but instead just sort of speak to the community. So I'm gonna use this opportunity to sort of challenge and even potentially provoke a little bit, with the goal of thinking about where we need to go next. So we'll go from a very, very positive and inspiring to a potentially more controversial and negative talk. I hope that's okay. The question I want to ask is, what data infrastructure do we need for open science? So I think everyone here is probably on board with the idea of open science. I've tried to sort of explain how I think of open science in pseudocode, right? We would like, if open science is successfully realized, this will mean that anyone in the world can verify, reproduce any scientific discovery, and can then extend and build on that scientific discovery. There's also sort of like more collaborative version of this that says any two scientists, or not even scientists, any two humans who want to work together on science anywhere in the world can do so and create new knowledge collaboratively. If we could make this happen, if we can make this a reality, we would really transform the world by really allowing all of humanity to participate in the scientific process. So I want to ask, what are the barriers to realizing that vision? Now, in the open science community, we have this mantra, FAIR, right? Findable, accessible, interoperable, reusable. And my goal here is not to criticize FAIR. FAIR has been incredibly impactful in giving very clear guidance to data providers and other services about things like use of persistent identifiers, embracing standards. But I want to suggest that FAIR is not going to get us all the way to open science. FAIR is great, nobody can disagree with FAIR, but it's not very specific, right? So making data-intensive scientific workflows fair is much easier said than done, because FAIR does not actually specify what protocols, what technologies, what infrastructure we need to build. So one way of summing this up is FAIR is not actually a platform, okay? Now, I use this word data-intensive science, and I just want to sort of articulate what I mean by that. So there's sort of two types of, I guess, large-scale science that we think about. Simulation is one, where we start with like some known equations, like the Navier-Stokes equation. We simulate them on a supercomputer, and what comes out is some data, right? Some results of that simulation. And data-intensive science, I think of sometimes goes in the opposite direction. We start from some big data set, we're trying to boil it down into some insights. And so Colette's presentation was a great example of what I would call a data-intensive science workflow, starting from a bunch of Landsat data, boiling that down into insights about how the Arctic ecosystem works. And these are quite different types of workflows, right? So simulation is generally a known computational problem with a well-studied algorithm and a standard architecture that it can run on, right? So we're actually very good in our community at running models, can generate tons of data that way. Data-intensive science is a little bit more open-ended. It's exploratory. There's a human in the loop. Visualization is a big part of data-intensive science. And the computational patterns and algorithms are highly varied and changing rapidly. Machine learning is a big part of this now. And there's really no standard architecture or platform on which to run data-intensive science. So I'm going to focus on this data-intensive science aspect because that's where a lot of my own research lies. That's where I see a lot of research today happening. So I'll put this claim out there. This may not be true, but I think it's a useful sort of foil for us to think about. I think open science needs a platform in order to be successful. The word platform is very overloaded. Everything's a platform these days, but platform does have a specific meaning in technology. A platform is something you can build on, right? So, iOS App Store is a platform. If you build an app that runs on the App Store, everyone in the world can run that app on the platform. And so that's a democratizing feature. Say what you want about the iOS App Store. It is a platform that is effective at doing what it's supposed to do. So what would it look like to have a platform where we could just run an open science project? Like if I could just run, Colette's project, just open it up and run it and build on it, right? That's what an open science platform would do. For open science to really take off at a global scale, everyone in the world needs to be able to access that platform, right? Just like everyone can access, basically everyone in the world can access Facebook. Everyone in the world can access certain internet services. To really democratize open science, we need to have an open science platform that everyone can access. And I think this is fundamentally why a lot of us are excited about cloud, not because, of whatever latest, cool service has been offered in AWS or whatever, but this idea that it is globally present and in principle anyone can access it. But the cloud itself is not an open science platform. It's more of infrastructure that a platform could be built on. And the key question I want to ask is, does the open science platform itself need to be open? I misunderstood my mandate here, and I prepared a 45-minute talk, and I don't have 45 minutes. And so this was the outline I had. And in order to sort of fix this, I'm going to skip the third part where I talk about PinGeoForge, which is a sort of project we have. I think many of you heard me talk about that in another session, so I'll just jump over that and try and finish on time. So I want to start by just kind of reviewing what sort of infrastructure we have today to do science on. Okay, and I'm speaking from the perspective of like a university scientist. Just quick show of hands, how many people in the room either work for a federal agency or work for a contractor who primarily works for a federal agency? Okay, so just look around, right? Realize how heavily biased the room is towards that audience, right? Most scientists are not working for a US government federal agency, we're at a university. That's where most research is happening. And this is the kind of infrastructure that we have access to. A laptop, a server in the closet, a departmental HPC cluster, or some agency supercomputer. That's what we can run on. And as we go sort of on one side towards the supercomputer, we get more resources, simultaneously more security and more constraints that limit what we can do. So what can we really rely on today as infrastructure? What can we assume everyone has? Unix operating system. Everyone can access one. Files. We assume everyone has a file system, a hard drive. We assume people can run a programming language like C, Fortran, Python, R, or Julia, and we assume they have bash scripting. That's about it. That's the only thing we can count on that's going to be present at all of these locations. Some of these things have the ability to run batch jobs. Some of them are on the internet. Ironically, the HPC systems that are most powerful are mostly just not even connected to the internet, right? Globus is pretty widely adopted, but not everywhere. I don't know of anyone who uses higher level data services or APIs or anything like that to query data. It just in academic research just doesn't even exist. So the infrastructure we have today to build on is extremely limited in terms of what we can assume people have access to. And this leads to the download model of science. This is why we do it, because it's something we can assume everyone has and that works for everyone. We download our data to some computer, then we analyze it. You've seen me do this before. This doesn't work with large-scale science, right? So what happens at places like Columbia is that we create what Shel Gentiman coined as a data fortress, right? We have a lot of resources. We want to do science, so we get a bunch of data from all the data providers, and we stick it on the cluster in our basement. And now, we have access to it inside our fortress. Have you ever tried to share code with somebody and the code looks like this? Right? This is, and then you're stuck. The reproducibility has now halted, right? So this works great, for one research group, but it's not a way we can move towards a more collaborative way of doing science. So here's sort of my summary of problems with the status quo. We've heard a lot of people sort of hating on files as a medium of data exchange, and I agree. I think we have to start thinking beyond data as files. There's a lot of data wrangling involved in downloading data, huge amount of toil and effort. Doing data-intensive science requires a lot of infrastructure. I mean, you need to be able to store the data, process it, compute on it. Many people in the world who we want to be involved in the scientific process don't have access to that sort of hardware. This data fortress thing really limits collaboration and reproducibility. Limiting access to outsiders is a feature, not a bug of that system, right? Literally the mandate of my IT department is to make sure outside people cannot come in and access our systems. That's their job. Right? So that's completely opposed to the idea of sharing and collaboration. And then each of these fortresses is kind of a special snowflake. They all work a little bit different hardware and software setup. It's very hard to transfer a project from one to another. If you've ever tried to move your project from one HPC system to another, you know what I'm talking about. It probably just didn't work out of the box. Okay, so what about cloud? And yes, I think cloud in general is our way out of this. In 2017, I participated in an NSF sponsored panel that produced this report called Enabling Computer and Information Science and Engineering Research and Education in the Cloud. And we identified a bunch of barriers that are limiting adoption of cloud. There's these sort of financial, political, sort of institutional issues that makes it very hard for us as academic scientists to purchase and get access to cloud computing resources. We're so set up around buying hardware, it's very hard to change that approach. Also, just beyond that, cloud is very complicated, right? The services that are offered by cloud computing, you go to the AWS dashboard, those aren't the things scientists need. They're too low level. So this report said we need a higher level layer of services to be developed. European scientists are basically forbidden from using US-based cloud providers. So while we go all in on AWS, For the most part, our European colleagues are literally forbidden by their funding agencies and governments from using those same cloud providers. So it's not a universal global solution. And unfortunately, not much about this has really changed for university scientists since 2017, when we contributed to this report. Agency, yes, NASA, you're making huge strides towards cloud. But I argue that the university community is not really coming along. Part two of this is I want to look at what are the elements that are maybe emerging today as an open science platform using cloud computing. Okay, so let's look first at some of the most impactful tools for collaboration. Raise your hand if you've used one of the tools on this screen. Okay, Google Docs is probably just the most impactful tool that's out there for collaboration, right? I mean, just in terms of actual usage, I love Overleaf. We all love and use GitHub. This whole meeting's broadcast on Zoom. These are amazing tools for open science and collaboration. None of these is open source in any way, right? These are commercial proprietary SaaS applications that we subscribe to and pay for that enable our open science to happen. So I just want to kind of note that paradox. And we have no trouble finding a way to pay for them, right? Like my university gets us a subscription for Zoom, I can pay for GitHub with a grant, something like that. I want to contrast this from what we've developed in the Pangeo community, which is very much a participatory, community-driven approach to building data infrastructure for science. So I'm not going to give like a full overview of Pangeo, what it is and what it does, but I really like to think of it as a process. Pangeo is an iterative process that's been going on for several years now, starting from scientific users and use cases who have science questions and challenges that are not able to be done with our current tools. We work as a community on developing open source software libraries, tools like Jupyter, Xarray, Dask, Czar, contribute new functionality to those tools, and then deploy them on top of HPC or cloud infrastructure to create sort of full end-to-end workflows for data-intensive science. We got into cloud by accident, Pangeo, right? So we didn't set out to do cloud computing. What actually happened is that our program manager, when we first wrote our first proposal, told us that we had to trim our budget. And so we had budgeted for a bunch of servers to build a data fortress, in the basement at Columbia. And so we cut that and we said, how about you guys give us some cloud computing credits instead? And that was extremely fortuitous because what happened is we kind of just got we got $100,000 worth of Google Cloud credits. And we just got to play. No one was really monitoring how we used them. We didn't have to be careful or, no one. In fact, I found out in retrospect, my university wanted to know about that and count it as a donation. But I never told anyone at my university we even had this money. We just did what we wanted and we granted anyone access to the project. And that was awesome because what we developed was a cloud native stack for data intensive science in the cloud, which looks something like this. When people say, I'm using Pangeo in the cloud, it usually means they're using this set of tools. Cloud optimized data format like Czar, distributing computing in parallel using Dask, interacting with data with a high level data model and API like Xarray, and talking to the cloud through Jupyter in a web browser. So this pattern has been pretty successful. We see individual scientists working this way, and we see big agencies and companies like Microsoft, European Space Agency. I saw a lot of usage of this technology stack in NASA. People don't always call it Pangeo, right? But if it's Czar, Dask, Xarray, Jupyter in the cloud, this is a pattern that our community developed, right? So we see this getting adopted, and it's having an impact. But I see a lot of limitations to the way we're doing things today. So this Pangeo has ultimately developed software, okay? Open source software, contributed to a lot of existing software, wired it together. Now that software can be deployed into a platform, right? So you can spin up these Jupyter Hub environments, and connect them to analysis-ready cloud-optimized data in the cloud. But there are many, many distinct deployments of this platforms. Dozens of similar yet different Jupyter Hubs with different configurations, environments, and capabilities. So just at this meeting, I've heard about, NASA's got different DACs have different, Jupyter Hub environments. Many different groups have their own Jupyter Hub. I right now have an account on about 4 or 5 different Jupyter Hubs in the cloud, where each has different software and different, capabilities and resources. So sharing projects between those hubs is still kind of hard. There's more interoperability, but there's still to some degree siloed pieces of bespoke infrastructure rather than a universal platform. And deploying those hubs requires quite a bit of customization work, right? So it's not just a thing you can run out of the box, although there's been a lot of progress in that direction. There's no sort of Pangeo as a service. You just click a button and you have access to this infrastructure. And then another major roadblock is that actually getting data into the cloud in this ARCO format can be very difficult, full of toil. An alternative approach to that sort of participatory, community-developed infrastructure are these vertically integrated platforms. So we heard about Google Earth Engine already. It's a very powerful tool. Amazing science has been done with it. There's other platforms like that out there. Descartes Labs has a platform for doing global scale geospatial data analytics. Sentinel Hub. This is a different model, but this is a very effective way to deliver infrastructure. If we could be sure that everyone in the world could have access to Google Earth Engine and it would be maintained in perpetuity, that would maybe be a great choice for us to just align on that as our platform for open science, at least in the geosciences. There is a different pattern, though, that I'm not sure that people are aware of here, but that I've been paying a lot of attention to, and it's called the modern data stack, right? So in the past 5 years, since we gave that, that report, industry, business analytics have moved strongly into the cloud as well. And the business community needs infrastructure and is willing to pay for it, right? And so what has emerged is a platform of software as a service elements that come together in what is commonly called the modern data stack, which is centered around the concept of a data lake or a data warehouse with many different tools and services that all connect to that data warehouse. This is a very effective and very standard pattern in industry. And I think it's interesting that basically no one in science is using any of these tools, but I think we need to be looking at it more, right? So here's like another diagram with some logos about some of the companies in this space. So, Snowflake, Databricks, Google BigQuery, like these are data warehouses, right? This is a pattern that's, instead of a monolithic platform like Google Earth Engine, there's different components. They're still provided by commercial vendors, but they integrate together through standards and APIs. So I think this is what a lot of us actually have in mind when we envision interoperability, right? The I part of FAIR. Okay, so this is the part I'm kind of gonna skip in order to end on time. We've been trying to develop our own software as a service tool called Pangeo Forge. And basically the point of Pangeo Forge, I'm gonna skip over all of this, is to solve this problem. We wanna get data into the cloud in an analysis-ready, cloud-optimized way so that many people can compute on it at the same time using the scale and the compute power of cloud computing. It is a democratizing effect to get data into the cloud this way, and I think many of you kind of see that. The problem is it's very hard. It takes a lot of engineering and scientific expertise to do this on a data set by data set level. So what we're trying to do is empower scientist users who may not be experts in data infrastructure or data engineering to create their own analysis-ready data in the cloud. Okay, that's what PangeoForge aims to do. So the goal is to just allow a data scientist who understands a data set they want to work with to create a recipe to bring that data into the cloud. I'm not going to go through these details. Skip over how this actually works. What we want to do, ultimately, the outcome we want to have is create a platform for collaboration around data curation that is all happening within GitHub. So these recipes for ingesting data are all stored in GitHub, and the community can come together, make new suggestions, work together on them, and we can all see sort of the provenance of where this data is coming from. This was this video won't play, but it's of this like failed Rube Goldberg machine that kind of describes where we're at today. It's very hard to build like software as a service that has the level of professionalism and functionality that we expect as like an open source, sort of open academic project. I mean, we're used to working with things like, you know, Google Docs, which, you know, it's like the professionalism of SaaS tools, commercial SaaS tools is so hard. But we're trying, we've been making progress, and I encourage you to check it out and learn more about it. This is just one piece of the puzzle, but it's a piece that we've been trying to solve. Okay, so I got to wrap up here. I've sort of thrown a lot of different ideas out, raised some questions about how we're approaching things today. Now I want to give a sense of where I think we're heading and what we need to be building together. Okay, so I think we've identified a very effective sort of general pattern for cloud-native scientific data analytics, right? It starts with analysis-ready, cloud-optimized data. We've heard a lot about that at this meeting. There's a lot of work happening on this and a lot of progress. We couple that with data-proximate computing. Bring the data to the compute. And by far, you know, I think the dominant way this community is doing that is through Jupyter, right? It's just an interactive data science environment that sits in the cloud where you can run your favorite programming language and all your favorite open source analysis libraries. That combination alone solves so many use cases. It's very simple, and simple means scalable and repeatable. The third element, though, to really do large-scale analytics is some sort of elastic distributed processing. So we need a way to scale out and process a lot of data. And there's a lot of cool technologies out there. And, you know, I think we should be experimenting more with these and trying out different ones. But these are the basic elements. And a key part of this architecture is the idea of separation of storage and compute. And this is really different from the way our status quo infrastructure works. In my data fortress, you know, we own the hard drives, we own the computers, and we're all, you know, it's all bundled together, right? The cloud allows us to do something really simple and transformative, which we call sort of multi-tenancy, right? We can have one copy of the data, say that's owned by Noah or whatever. Many different users can come and compute on that data using their own bill, their own cloud account, right? And this is a sort of gateway to that sort of scalability and sort of platform style features of you know, that we need for an open science platform, right? So you know, if you put this all together, you can start to see like this is kind of what the emerging open science platform looks like. We've got data in the cloud, got these compute environments accessible through Jupyter. We also have a lot of people here interested in building higher level services, dashboards, apps, et cetera, that sort of will, you know, talk to this data. And I think we can think of that, I think of that as just a different layer. Jupyter is one front end we can use to access our data interactively. We can build data apps or dashboards using all the same sort of lower layers. It's just a different sort of skin on access to the data. And this type of environment can really run on any you know, modern cloud-like platform, and can also run on premises on any internet-connected system. So I really think it's the right foundation. And you know, if we see, like, what I like about this is it's extensible. We can build a federation this way. People can add capacity to the system by providing new data or providing new compute resources. The key here is to make those resources similar enough that we're not building more silos, but are instead growing a federation of interoperable computing and data resources. And I think this community is kind of leading the way on this. Okay, the challenge I see here is how can we deliver this type of open science platform in a scalable, sustainable way? I think each group hiring its own DevOps engineers to build its own sort of customized Jupyter Hub environment is not the right way forward. I think some choices, we could embrace commercial SaaS. We could have a modern data stack for science where we just buy these elements as a service on a subscription-based way. We can cultivate this community-oriented, participatory SaaS model. This is how Wikipedia is run. This is how Conda Forge is run. This is how Binder is run. The organization 2I2C, International Interactive Computing Collaboration, is trying to pioneer this way of running Jupyter Hub. And our Pangeo Forge project aims to be this sort of participatory software as a service model. The reality is we probably need a mix of both, and it's great to see folks experimenting with all kinds of different models. So my final challenge that I want to identify here is data gravity. So data gravity is the ability of a body of data to attract application services and other data. So once there's a lot of data in one place, stuff starts to just accumulate around that data. Right now, AWS probably has the most data gravity in our world, but there's plenty of other gravitational bodies, right? So Microsoft and Azure is making a big play for data. There's certainly plenty of data in Google, and Earth Engine is a big part of that for our community. Then there's Europe, right? They have a very different approach to data infrastructure. They have not embraced commercial cloud the way the US has, but some of our most important environmental data is coming from the Copernicus program and European agencies. And I haven't even mentioned other regions, but they have their own issues here. So where's this all heading? Right? What is the stable, steady state solution for this data gravity problem? Are we eventually all going to end up in AWS or one of the other commercial cloud providers? I think that's probably not what the science community wants to see happen, despite the value of those partnerships that we have. So what I think we need is some sort of global scientific data commons that lives actually outside of the commercial cloud, but is closely interconnected with it, right? And we see a lot of emerging elements of this. So the ESGF, Earth System Grid Federation, is an example of this sort of federated infrastructure. Open Storage Network is another new project in this space that I think has a lot of promise. This is a place where we can sort of dip our toes into the Web3, decentralized web world, crypto. You know, despite all the horrible things happening in cryptocurrency in terms of mining and wasting energy, there are some really interesting ideas about how to decentralize the internet and how to distribute data and services in a way that doesn't put everything into just one service provider. So I think we need to be engaging with those communities and learning about their tools. So I think that's it. I want to shout out a bunch of great organizations I know who are working on this open science platform stuff. It's hard work, it's very difficult to do in an academic environment, and people are making some great progress. And so I think the future is very bright. I'll kind of just end there with a plug for our Pangeo community, where a lot of these issues are being discussed and a lot of these tools are being developed. And if you want to engage with any of this, I invite you to come check out our resources and join our community. So thank you, and sorry for going long.
Thank you so much, Ryan. I know that we could probably stay here for another 45 minutes of Q&A after a presentation like that. But we don't have 45 minutes, but we will try and get a couple questions in. So vote up the questions that you like, both here in the room and online. We'll start with the first question. At what point in a student's education should we integrate these open data principles? K through 12, undergrad? What are your thoughts on that?
Ooh, great question. I didn't even learn anything about data principles as a PhD student at MIT. And I didn't learn about data licensing, I didn't learn about data formats, I didn't learn about any of that. So as far as I can tell, it's not in the curriculum at all at any level. Yeah, it would. I think a great place to do this is in the undergrad level. I think we need instead of a sort of traditional computer science algorithm curriculum focused on sort of algorithms and data structures, we need to really be teaching about the building blocks of open source, open data, and collaboration as a foundational skill for being part of scientific research. So that's where I think it would be good to do required course on data licensing and intellectual property for all undergrads.
Excellent. I think I saw some Funding Friday pitches that might help us get there. Great. Can you speak more to the European restrictions for AWS and other cloud services?
To be honest, not really. I just know that they have restrictions, and you're probably best off like talking to someone from Copernicus or one of those agencies to get a definitive answer on that.
Great. All right, let's get another question in there. Can you comment on proprietary software, MATLAB, IDL, in open science?
Yeah, this is a great question. I identify as like a sort of big open source, open science advocate, but I'm now becoming more and more aware of how much proprietary tools are embedded into everything we do. That's why I like to highlight, like GitHub is, it's not actually open source in any way, right? It uses an open protocol. I think where I get stuck on MATLAB and IDL is that like, it's a real barrier to participation. Because many people in the developing world just can't afford those tools. If those companies would adopt a different model to sort of software distribution, maybe it would be more of a an option. At this point, as I feel very strongly, the open source software ecosystem between R, Python, Julia, the capabilities that are offered far exceed what is available in those proprietary science tools. So I wouldn't, I don't choose to use them.
Excellent. Thanks so much, Ryan. We will have a coffee break after this session, so hopefully you guys can all continue the conversations over a cup of coffee. Now, I would love for Denise Hills to come up to the stage and let us know the results of Funding Friday.
I think we have slides. I hope we have two. Oh, great. Oh, perfect. This is great. I also want to remind everybody that these are team presentations, and also I like having a mic. I don't have to shout at you all now. But first, I want to congratulate all the presenters of Funding Friday. We wish we could award everybody, but this is why the community voice is so important. So first, I want to recognize the 4 winners that we have from our teacher and student group. That is, if you're in the room, go ahead and stand up and wave when I call your name. Samantha Child, Carrie Suja, yay, there you are. Amruta Kale. I can't see anything in this room. There we go. And Chian Hoang. Congratulations, everybody. That's really great. And so our partners and other researchers, this is the first name that is on the poster. It is not necessarily who's receiving the funding. And if I remember who else is on there, I'm telling you. So C. Simonello, and that was Philemon as well. Is Philemon still in the room? I think Philemon had to leave. Elizabeth, oh, no, he's there, sorry. Like I said, the lights are right in my eyes, so I can't fully see. Elizabeth Joyner, Brian Callahan, Kathy Fontaine, and Ross Bagwell. Woo! Elizabeth was the one who was able to present today. Karen Moe, where's Karen? Congratulations, everybody. If you are here and your name was on one of these winners, we would love to get a group photo of you all, so kind of meet by the whiteboard by the registration desk after this. And in case you remember what the posters looked like, but not the people, these first 4 are from our teachers and students. Those are the 4 winners. And then the next slide, please. And that is those are the 3 from our research participants. So thank you. I don't know if Susan has any final words.
Just want to say thank you all for being here. It's really awesome to have a nearly full room for the closing plenary after a really big week, right? Coming back in person, giving all that energy out. I just thank you all for sticking through. We have a coffee break next, and then some great sessions not this afternoon, great sessions after the coffee break. Lunch will be served, and bring your lunch back in here. As you noticed this morning, we moved some things around a little bit. We've got some more friends across the way, so bring your lunch back in here for that, and then we really look forward to continuing to engage with you 52 weeks a year at ESIP, not just the 1 week in June and January. So find ways to get connected, and go out and have a great day and safe travels when you go home. Thank you very much.